Hello everyone, my name is Mustafa Can Macit. In this presentation, I will review and experimentally analyze the recent paper on 3D point cloud reconstruction. The selected paper is titled Structured Light Non-Coplanar Dual-Line Scan Camera System for Complete and Accurate Point Cloud Reconstruction in Variable Motion. It was written by Liuyao Me and his friends in 2025, and it is published in Elsevier. And the main motivation is 3D reconstruction for industrial inspection and quality control. It's in many real applications, the object moves during the scanning. If this motion is variable, the profiles are not stitched at the correct position. This causes stretching, compression, bending, or missing regions in the final point cloud. And the paper proposes a structured light dual non-coplanar line scan camera system to handle this variable motion problem. And this slide shows the hardware setup used in the original paper. The system uses two side-by-side line scan cameras. It also uses a high-speed structured light projector, and the auxiliary camera is not used for reconstruction directly. It is used only for the calibration. And during the scanning, the object moves through the viewing planes of the cameras. Each line scan camera captures profile information over the time. And the key point is that the system estimates motion during scanning. By estimating the motion, the paper reduces point cloud distortion caused by variable object movements. And in my experimental part, I did not reproduce the full industrial system of the paper. Instead, I built a simplified proof of concept setup. In the original paper, real line scan cameras are used. In my setup, I use standard area scan cameras. And the high-speed structured light projector is simplified as a single line laser source. The conveyor-like object motion is approximated using a 3D printer bed. In each frame, the laser line is detected and treated as an approximate line scan profile. The goal of this setup is to test the same reconstruction problem with my own data. More specifically, I wanted to observe the effects of motion error, calibration error, and laser extraction error. The slide shows the mathematical core of my reconstruction pipeline, and also related to the main principle of the paper. In both systems, a light profile is observed on the object surface and converted into 3D points. In the original paper, structured light profiles are obtained using line scan cameras and a projector. In my simplified setup, I use a laser line and two area scan cameras. First, I detect the laser stripe in both camera images. For the same laser point, I obtain one pixel coordinate from the left, one from the right. These are represented as PL and PR. After stereo calibration, I know the projection matrices of the left and right cameras. These are represented as PL and PR2. A real 3D point must project consistently to both image points. Using these two views, I solve the 3D point by triangulation. Repeating this process for every detected laser point gives one 3D profile. Then, as the object moves on the 3D printer bed, consecutive profiles are stitched into a complete point cloud. So the common idea with the paper is profile-based 3D reconstruction. The difference is that the paper uses a light scan camera and a projector-based structured light, while my implementation using a stereo camera and a laser line approximation. Before testing the dual camera setup, I first tested the main motion problem with a simpler cup experiment. This was a monocamera laser scan. The purpose was to show what happens when the motion information is wrong. In this setup, each frame gives one surface profile of the cup. If I assume the wrong speed, the spacing between profiles becomes wrong. As a result, the reconstructed cup becomes distorted. In the middle image, the speed assumption is wrong. The cup is stretched and the geometry is not compact. In the right image, the speed setting is improved. the reconstructed cup becomes more compact and more realistic. This simple experiment shows why motion estimation is necessary. And the motion must be estimated, not assumed. After the cup experiment, I tested a more complex object, a keyboard, like paper. In the dual camera sense, the paper is much harder than the cup. It has sharp edges, gaps, keys, dark regions, and repeated structure. These properties make laser extraction and 3D reconstruction more difficult. In this experiment, two cameras observed the laser line from different viewpoints, like the paper did. The 3D printer bed provides controlled object motion. This experiment tests both calibration sensitivity and profile stitching sensitivity. The result shows that the keyboard structure can be reconstructed to some extent. However, it also shows noise-missing regions and sensitivity to calibration. This means complex geometry makes the reconstruction problem harder. But actually, we can see that the keyboard is reconstructed very well when you know the original speed of the bed. And if we come to the failure case, this slide shows a failure case using the cup object. Here I intentionally show what happens when the main assumptions of the reconstruction method are not satisfied. In the left result, the camera calibration is poor. Because of this, the reconstructed points from different views do not align correctly. The point cloud becomes scattered and geometrically inconsistent. In the right result, the alignment is better compared to the left case. However, the reconstruction is still incomplete because some laser profile points are missing. This shows that calibration alone is not enough. The laser line also has to be extracted reliably. So this cup example demonstrates two important failure sources: poor calibration and incomplete profile extraction. This slide focuses specifically on calibration quality. On the left, the calibration is relatively good. The keyboard shape is more coherent and the reconstructed point cloud is more consistent. There are still missing or noisy regions, but the general keyboard structure is visible. On the right, the calibration is poor. The reconstructed points are shifted and misaligned. This causes the point cloud to lose geometric consistency. This comparison shows that dual camera reconstruction is highly sensitive to the relative pose between cameras. Even if the laser line is detected correctly, wrong calibration can still produce a wrong 3D reconstruction. This is why accurate calibration is one of the key requirements of the paper. To summarize, I observed four main failure sources. First, poor camera calibration causes the two viewpoint clouds to be misaligned. Second, wrong object or profile positioning shifts reconstructed points away from their expected locations. Third, unreliable laser extraction converts false image pixels into false 3D points. Fourth, occlusion and repeated geometry cause missing or ambiguous reconstruction. The key message is that the method does not fail randomly. It fails when its key assumptions are violated. In conclusion, the paper proposes a robust solution for 3D reconstruction under variable motion. I tested the same problem with a simplified setup using area scan cameras, a laser line, and a 3D printer bed. The CAP experiment shows what wrong motion information causes stretching and compression. The dual camera experiments show that the poor calibration causes misalignment between two camera views. These failure causes explain why the paper needs accurate calibration, dual view matching, and motion estimation. The main takeaway is that accurate 3D reconstruction requires correct profile measurement, correct camera geometry, and correct motion estimation. Thank you for your attention.